Okay, so we're going to continue on lecturing here, chapter 8. Last time we started talking about Avogadro's number, grams, moles, and the really important sort of conversion factor of really molar mass, which we get from the periodic table. And that's how many grams per mole there is. And that's, again, a conversion, as we talked about last time, that we do a lot here in chemistry. Uh, we did a number of examples last time, but I did want to also talk about another sort of variation on that sort of calculation that we did last time, just so you would know how to do it as well. So let's talk about if we had something like, I don't know, we'll go 125 grams of C2H6O, which I think we used earlier. And we wanted to know how many atoms of hydrogen are there. So this is also sometimes a question that you're asked where you're given a chemical formula like this, and you're maybe not interested in the entire thing, but you may be interested in one of the elements that are there in the actual formula. So in this case, we're actually interested in just the hydrogen, not the entire ethanol here. So we do need a way to go for sort of the whole thing to just that particular element. And we could actually use the chemical formula as a conversion factor to do so. So what we would do is when we look at this formula here of C2H6O, and we look at all these bottom numbers, these subscripts, these are also sometimes referred to as the moles of each of these guys. And what that will allow us to do is actually come up with several different conversion factors that you could use based on just the actual formula itself. We could say, for example, in 1 mole of the entire thing, there would give me 2 moles of just carbon. And again, that 2 would come from the little 2 that's on the bottom. We could also say in 1 mole, this entire thing, it would give me 6 moles of hydrogen. And if we were actually interested in oxygen in this case, we could do 1 mole of the entire thing would tell us that we have 1 mole of oxygen. So we could use these sort of like mole to mole relationships as conversion factors to go from the whole thing to just the element we're interested in. In this case, though, in order to use it, since it is a mole to mole relationship, we would, in this particular case, has to first convert our grams of the entire thing into moles. So just like we talked about last time, to do that, that is the molar mass, right? So that molar mass is our conversion factor that we get from the periodic table to go back and forth between grams and moles. Remember that Avogadro's number is the conversion factor that we use to go from like moles to atoms or moles to molecules. And we don't necessarily have to use that in every case. So here we'll add up our molar mass of our C2H6. And I think we did it in an earlier problem, but just again, to remind you, these numbers are coming from the periodic table. The number on the bottom, which is referred to as the molar mass of each of these elements, and in this case, 16 grams per mole. And again, this would represent really our carbons there, our hydrogen, and our oxygens in this formula. I think that was like a 4607, if I'm not mistaken on that. 2 times 12.01 plus 6 times 1.008 and a 16, 4607. And remember, that would be the molar mass. And another really important thing that we talked about last time in terms of molar mass is whenever you're calculating molar mass or need to use it, it is always based on just the formula by itself, right? Regardless if there might be a coefficient in front of it or anything like that. If you just take the formula, that is how you calculate the molar mass. And that's why the molar mass is how many grams there are per 1 mole of something. That 1 mole means basically just one of the formulas by itself is what you're calculating. So we will do our calculation here. We'll take our 125 grams of the whole thing. We will use our molar mass here to convert the grams of the whole thing here into moles. And if I stop right at this point, I'm in moles of the entire thing. And again, in this particular problem, we're interested in just hydrogen. But what we just did now allows us to use our relationship that we got from the formula to go from the whole thing to just the hydrogen. So that would be the next step that we would want to do. Again, opposites here cancel. So our 1 mole of the entire thing will give us 6 moles here of hydrogen. At this point, the moles of the entire thing will cancel, and now we're in moles of just the hydrogen. Now, if I wanted to know the moles of hydrogen, I would be done with my calculation. I could just obviously calculate and get a number. If I wanted grams of hydrogen that are there, I would then use the molar mass of just hydrogen at this point. But in this case, we're actually not interested in either of those. We're interested in atoms, right? Which is sort of the key word we talked about last time that tells us we need to use Avogadro's number here. So this is where we would want to use Avogadro's number, which is our 6.022 times 10 to the 23 atoms of hydrogen equals 1 mole of hydrogen. So we're going to use that as a conversion factor here to finish the problem. We want the moles to cancel. So our mole of hydrogen on the bottom, Avogadro's number there up on top, which would be our atoms. The moles of hydrogen cancel, and now we're at atoms. To get our number here, we'll multiply across the top there, 125 times 6 times 6.022 to the 23. We'll divide by 4607. And in this case, we will get 9.80 times 10 to the 24 atoms of hydrogen. So a lot of hydrogen atoms in that particular sample. So this is a very common thing that you sometimes come across where you're just doing maybe basic sort of grams to moles calculations where you may need to use the formula itself as a conversion factor. And again, those little guys on the bottom can be thought of as the moles of each of those elements. And it allows you to go from the kind of the whole thing to each of the individual elements. Any questions on that calculation there? Obviously, again, in this case, we use Avogadro's number because we were looking for atoms. But as I said earlier there, if you're looking for moles, you could stop there or use the molar mass at the end to get the grams as well. Any questions on that version of the calculation there? Okay, then let's talk about, speaking of formulas, let's talk about some important formulas. But before we do that, let's talk about percent composition of a compound. So molecular formula are formulas where they basically will tell you exactly the number of atoms there are in a particular compound. It will usually tell you the exact number of atoms that there are of each element. A molecule, as we've talked about before, again, is basically a basic definition of 2 or more atoms together. They could be the same element, they could be different elements. Chemical formulas, and especially molecular formulas, as we will see here in just a second, sometimes will give you a lot of information about how everybody's sort of connected together. And sometimes it is just a basic formula of these are the elements that are there. And it really doesn't sort of tell you how things are connected or put together. So when we look at a molecular formula, the simplest molecular formulas that we have seen or come across are those diatomic molecules because they only have like N2H2, 2 things present. Now, if we look at ethanol like we were just looking at, we see the 2 different formulas down there. It's the C2H6O are the CH3 CH2OH formula. They are both represent a molecular formula for ethanol. The only real difference between these two is the second one gives you a lot more information about how the thing's sort of connected. If you were to draw ethanol, it would look something like this. So you can see that basically the second one, which is also sometimes referred to as a structural formula, you have CH3, which is the CH3. You got your CH2 next. CH2, which is the CH2 there. And lastly, we can see that we have OH minus, which is the OH minus. So definitely the second structure, our formula there, gives you a lot more information about the structural way that that molecule is put together. The other one is just like, hey, there's a 2 carbons, 6 hydrogens, and 1 oxygen involved. You might not understand exactly how it's put together. And sometimes people do get very much confused when they see formulas written different ways. They think they are actually 2 different things when they're actually the same thing. Another common example is our friend acetic acid, which is basically the main component of vinegar. And acetic acid is written like this, or sometimes it's just written like this. And they are, again, basically the same thing. The second one down here gives us a better understanding of how it's put together, which if you drew acetic acid, it would look something like this. It's an organic acid. And you can see CH3, which is our CH3. And this COOH is basically this group right here, which is referred to as a carboxylic acid group. And again, much more structural information than from that. You might not be able to really figure out how it's sort of put together. So sometimes molecular formulas give a lot more information about things than just what's there. But the basic molecular formula is just simply what elements are present and how many of each of those that there are. Any questions on that there? Now, the empirical formula, on the other hand, is the simplest whole number ratio of elements that are present. So if we look at hydrogen peroxide, essentially we have 2 hydrogens for every 2 oxygens that are present. And if we were able to divide everybody by 2 here, that is the same as saying you have 1 hydrogen for every 1 oxygen that's present. And that would give you your empirical formula here of our HO for our molecular formula that is present. Now, sometimes the molecular formula and the empirical formula are going to be the same, because one thing that you cannot have is when you look at these subscripts on the bottom, they do have to be whole numbers, because you can't have like a half atom or a quarter of an atom or anything like that. So they do have to be whole numbers. So for example, if we looked at water, that is basically 2 hydrogens for every 1 oxygen, which means there's no way to reduce that down any further and still have whole numbers. So something like water would be both the molecular formula and the empirical formula. One place where we always see an empirical formula is with ionic compounds. Ionic compounds, which have our cations and our anions. When we talked about it, right, we put it together in the simplest way to get to 0. Like if we had calcium and chloride, we would need 2 of these guys to give us calcium chloride. So empirical formulas for ionic compounds are pretty much what they are, because that's the way we put them together. The simplest way to get to 0 will give us the basic empirical formula. Empirical formulas are also ones that you find in lab, because essentially all you have to do is basically do some mass measurements, and differences in mass will allow you to do some calculations like you might do later today, and you'll be able to figure out the empirical formula of a particular compound. Any questions on that there? Here's another couple examples here. Again, our N2H4, that is 2 nitrogens for every 4 hydrogens. With clearly, we could divide everybody by 2 and end up with 1 nitrogen for every 2 hydrogens. And that would give us our empirical formula that we see there in our simplest whole number ratio. And again, a few examples here. There's no way to reduce down this any further to get whole numbers, or this, as we have a 1 to 2 relationship or a 1 to 3 relationship. So again, in each of those cases, that would be both the empirical formula and the molecular formula. All right, so why don't you take a moment here for each of these. What is the empirical formula if these are the molecular formulas? Okay, so let's take a look at this one. So if these are our molecular formulas here, in the case here, we have 2 carbons and 2 hydrogens, which means we could definitely reduce everybody down by 2, which would give us 1 carbon and 1 hydrogen, which would be our empirical formula. Here, when we look at I2O5, we got 2 I's for every 5 oxygens. That's pretty much as far down as you could go because there's no way to still get whole numbers. So that would also be our empirical formula in this case. And lastly, we got 6 carbons for every 12 hydrogens for every 6 oxygens. We could clearly take everybody here and divide by 6, which would give us 1 carbon, 2 hydrogens, and 1 oxygen as our empirical formula. So again, it does need to be whole numbers. And as the case in the middle there, sometimes you can't get any lower than what you have going there. So this is the way you would calculate the empirical formula if you were given the molecular formula. You just basically need to reduce it down to as simple as whole number ratio. Any questions on that there? Okay, so then let's talk about percent composition by mass of compounds. So percent composition by mass of compounds means basically we're just going to try to find the percentage of each element that's present, for example, in a formula. So to find the percentage of that element, we would take the molar mass of that element that is there in that particular compound. We would divide it by the molar mass from the periodic table of the entire compound. And we would times it by 100%. So here we would want to figure out the molar mass of the particular element divided by the molar mass of the entire compound times it by 100. When you add up the percentages of all the elements present in a particular formula or compound, it should equal 100, right? That way you're not missing any element along the way, or it should be really, really close to 100 when you're doing so. So if we take a look, for example, here at hydrogen peroxide, and we wanted to calculate the percent composition of hydrogen and oxygen in this case, the first thing we would want to do is go to the periodic table and calculate the molar mass of it. So we have 2 hydrogens, each at 1.008 grams per mole. We also have 2 oxygens, each at 16 grams per mole. That's going to give us a molar mass here of about 34.02 grams per mole. Now that we have the molar mass of the entire compound, we can calculate the percentage of hydrogen by taking the amount of hydrogen that's there. So 2 times 1.008 grams per mole is the amount of hydrogen present, divided by the molar mass of the entire compound times 100%. And in this case here, we would have a percent composition for hydrogen of, we'll call it 5.926% hydrogen. We could do the exact same calculation for the oxygen to find the percentage of oxygen. There are 2 oxygens, so we want the mass of just the 2 oxygens here up on top. Basically our oxygen. And we want to divide it by, again, the molar mass of the entire compound and times it by 100%. And that would get us basically 32 divided by 3402, about 94.06% oxygen. In this particular case, we know that a majority of the mass of this compound is the oxygen, right? It's made up basically by mass, 94% oxygen, about 6% of hydrogen by mass. By the way, because this is the only 2 elements present, right, in this compound, once I had the percentage of hydrogen, I could have just took 100 minus that, right? And that would then give me the percentage of the other one, since that's the only other element that's present. So sometimes you can do that without having to do necessarily the calculation for each one individually, but you could do it for each one individually, because again, all the elements need to add up obviously to 100% by mass. Any questions on that? Now, earlier we saw that the empirical formula for H2O2 is HO. And if we wanted to do the percent composition by mass of our empirical formula, let's see if it's any different. So in this case, we have only 1 hydrogen, which would be 1.008 grams per mole. We have 16 for our 1 oxygen, which means the molar mass here of our empirical formula is going to be 1701 grams per mole. So if we do our percentage of hydrogen, in this case, just the 1, divided by the molar mass of our empirical formula here, times 100%. And if we do that there, we end up with our 5.926% hydrogen. We could also do the same thing for oxygen. In the empirical formula, there's just 1 oxygen, which would be 16 grams per mole divided by 1701 grams per mole times 100%. And in this case here, we end up with 94.06% oxygen. Is the percent composition by mass of these elements between the molecular formula and empirical formula, are they the same or different? They are the same because they're just the simplest whole number ratio of what's present. So you still have the same ratio of each of those elements, which would give you the same percentage by mass. So you could calculate the percent composition of the elements for the empirical formula or the molecular formula, and it should come out the same. Any questions on that there? No. All right, so why don't you try one here? What is the percent composition of each of these elements? In phosphoric acid, hydrogen is 1.008, phosphorus is 3097, and oxygen is 16. All right, so what is the percent composition of each of these guys? So again, we're going to start with the molar mass of the entire compound here. So we're going to go 3 times our hydrogen from the periodic table. We'll add it to our 3097, which is for our phosphorus, and we'll add it to 4 times 16, which is our molar mass for our oxygens. That's going to give us a molar mass here of 97.99 grams per mole. We could start with hydrogen here. So we have 3 hydrogens there. So that will go up on top from the periodic table. We'll divide it by the molar mass of the entire compound here and times it by 100%. And that's going to give us a percentage for hydrogen of about 3.086% hydrogen. We do the same thing for phosphorus. We have just 1 phosphorus in this formula, so 3097 divided by 97.99 grams per mole times 100% gives us here about 31.61% phosphorus. At this point, you do have 2 options. You can either add those 2 numbers together and take 100 minus it, or you could just do the calculation for oxygen at this point, which would be 4 times 16, which is how many oxygens we have in the formula, divided by 97.99 and times it by 100%. And that would get us about 65% here. Oxygen. As we can see, major mass contributor there is going to be the oxygen in this case, followed by the phosphorus. And if we add up all of our percentages, we are about at 100%. Yeah. Questions on any of those? So if you want to figure out the percentage of something in a formula, you could do something like percent composition by mass. Say if you had something like a hydrate, for example, right? Like this. By the way, hydrates are written funny like this. They have a little dot, which means they have 7 waters that are crystallized with them as well. You would take the mass from the periodic table of the 7 waters, and you would divide it by the molar mass of the entire hydrate, which is the salt part, the magnesium, the sulfur, and the 4 oxygens, and the 7 waters. So you would need to include the 7 waters as well. You take the mass of that hydrate and times it by 100%, and that would give you the percentage of water, for example, in that particular hydrate. Any questions on that there? All right, hypothetically speaking, you might do that next in a little bit. All right, then let's talk about how to actually calculate empirical formulas when you're not given the molecular formula. So when you're given some information, how you go about calculating your empirical formula. So to calculate your empirical formula, a lot of times you are given the percent composition by mass, like we just talked about there. So a lot of times you're given that. And whenever we have a percentage and you want to kind of turn percentages into sort of usable numbers, a lot of times we assume, in this case, 100 grams. And the reason why we assume 100 grams is that turns the percent number into the same number for grams. So if you had 50% carbon out of 100 grams, you have 50 grams of carbon, right? And so that's a way we want to do that. Once we do it and we get it into grams, the next thing we want to do is take the grams to moles of each of the elements that are present. And that's going to be the molar mass from the periodic table that we use, which are grams per mole, right? Periodic table. Once you have the moles of each element, you're going to divide by the smallest number of moles. So for example, let's just say we got to this part and we converted everybody into moles, and we ended up at this point with 2 moles of A and 4 moles of B. What we would do in this case is we would divide everybody by the smaller number, which is 2. And that will give me 1 when I do it here. That will give me 2 when I do it here. And if you divide by the smallest number of moles and you hit all whole numbers, are really, really close to a whole number, like 1.99, 1.98, or just above a whole number, like 2.01, 2.03, then that would be your empirical formula. So that would be your empirical formula in this case. It would be AB2. Now, you're not always going to hit whole numbers, unfortunately. So for example, let's say we got here and we had this arrangement of numbers. Let's just say we had 2 moles of A, but 5 moles of B. Now when I would divide by 2, I will get 1 here, but I will end up with 2.5, I believe, right, in this particular case. And 2.5 is not good because that will give me an empirical form of AB 2.5. And as we talked about before, you can't have like a half atom, right? You got to have a whole atom, and they do have to be whole numbers. So if you find yourself dividing and you do not get whole numbers, you then need to figure out a number to multiply this thing by to get to a whole number. So you could just do a basic trial and error. 2.5 times 1 is 2.5. 2.5 times 2 is 5. The factor at which I will multiply everybody by is the 2, not the 5. Yeah, so you want to multiply everybody here by 2. So we would take this empirical formula, multiply it by 2, and that will give me A2B5 as my proper empirical formula. So when you're calculating empirical formulas, you typically do not round unless it is like super close to the next number, like very, very close. Common ones where it is too far to round, you end up with something like 0.33, 0.5, maybe like a 0.25, 0.75. You end up with a number like that, like we did here, 2.5. That is too far to round. That's where you need to figure out a number to multiply everybody by to get to a whole number. Any questions on that there? All right, so let us take a look at one here together, see how this all works. So we have ascorbic acid, which is 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen. Really, the first thing you want to do when you look at a problem like this is to, again, take a look at the percentages, and they should, again, add up to about 100%. If you find yourself in a situation where they do not add up to 100%, you're probably missing an element, and there should be some way to figure that out, what's missing. But they should, again, add up pretty close to 100%. Because these are percentages, we're going to assume 100 grams, which is just going to turn our percentages into grams. So that would mean we have 40.92 grams of carbon. We have 4.58 grams of hydrogen, and we have 54.5 grams of oxygen. Now that we have it in grams, the next thing we want to do is convert everybody into moles. And we're going to go to the periodic table to do that. So the molar mass from the periodic table for carbon is 12.01 grams per mole. The molar mass for hydrogen is 1.008 grams per mole. And the molar mass for oxygen is 16 grams per mole. Again, each of those numbers come from our molar mass from the periodic table. So we're going to take 40.92 and divide it by 12.01. That's going to give me 3.407, and I'll call it 2 moles of carbon. 4.58 divided by 1.008 gives me 4.5437 moles of hydrogen, and 54.5 divided by 16 gives me 3.4063 moles of oxygen. Here, I'm not really ending my calculation, so I am going to really kind of take it to a few extra digits. You probably don't want to round too much when you're kind of doing this part of it. The next thing we want to do is divide by the smallest number of moles. And it is as simple as which one's the smaller number. And in this case, it looks like oxygen actually slightly beats out everybody in terms of being smallest. So we're going to divide everybody here by oxygen's moles, which is our smallest. That gives us essentially 1 there, gives us 1 there. And when we divide our 4.5437 divided by 3.4063, that gives us a 1.33 for our hydrogen. That would give us an empirical form of CH1.33O. Can I have 1.33 for my hydrogen? I cannot. And again, this is a place where it is too far to round. So we need to figure out a number to multiply everybody by to get to a whole number. So once again, 1.33 times 1 is 1.33. 1.33 times 2 is 2.66. 1.33 times 3 is 3.99. That looks pretty close to 4. That's pretty close enough to round. So once again here, we're going to multiply by the 3 as our factor. So we want to multiply everybody here by 3. So we're going to multiply everybody by that factor of 3. And that will give me C3H4O3. And that would be my proper empirical formula at this point. Any questions on that? So again, get it to grams, grams to moles, divide always by the smallest number of moles. If you hit all whole numbers, you're good. If not, you need to figure out that factor to multiply it by to get to a whole number. Any questions on that there? All right, why don't you try one then? Why don't you try this one? We have sulfur and oxygen. What is the empirical formula? Sulfur is 3207. And oxygen is still 16. Okay, so let's take a look here as we're getting to the end. We have to have a third number here, which is basically the mass of the sample that contains the sulfur and the oxygen. The purpose of that number really is for you to make sure when you take these two numbers, kind of like what we do with our percentages to make sure it adds up to 100. If we take these two numbers, it should add up to that number, which it does. Once again, if you did add those numbers up and it didn't add up to that 1.078, you probably again are missing some type of another element is there, and there would be some information to probably allow you to figure out, how much it is. You can find that other element probably by just subtracting the total from what you have. In this case, it does add up. They're already in grams, so we shouldn't go backwards. So next thing we really want to do is just convert these grams into moles. So again, we'll use our molar mass from the periodic table, 3207 grams per mole of sulfur and 0.538 grams of oxygen, 16 grams per mole of oxygen. In this case, 0.540 divided by 3207 gives us 0.016838 moles of sulfur. 0.538 divided by 16 going to give us 0.03363 moles of oxygen. In this case, it is the sulfur that is the smaller of the two. So we're going to divide everybody by the moles that we have for sulfur. That's going to give us obviously a 1 for the sulfur, and for our oxygen here, it will give us basically a 1.99. This again is close enough to round to 2, as it's pretty much on 2 in that case. That means we essentially did hit whole numbers, and that means that our empirical formula in this case would be SO2. Any questions on how to calculate empirical formulas? Yeah. All right. We will lay it up there, I think, for today.